he's going to actually show you how to do it. I don't know why I look angry right there. I'm not. But I'm going to now show you how to do a cloud in a bottle. So without further ado, take it away, Terrence.
Thank you, Terrence. Hi, everybody. So what I'm going to do right now is actually demonstrate what's called a cloud in a bottle. So I'm actually going to show you how to make your very own cloud. Now you can do this at home. There's not a whole lot that goes into this, but I also thought for the purpose of this lab I'd show you as well. Usually when I teach this lab on campus I show people. So here's what you need. So let me scooch in a little bit. So what you need is an empty water bottle like this, the little water at the bottom, and the reason why you need this little water is because this is where the water vapor that's going to saturate the air in the rest of the bottle comes from. Now with that said, I also have for this first part a temperature strip here. This is the same kind of strip that you can get at a place like an aquarium store. And if you take a look, we can zoom in just a little bit. Right now the temperature, not pretty warm, so it's 64 Fahrenheit or 18 Celsius. So here's what I'm actually going to do. To demonstrate how the cloud in a bottle works, I'm going to first just squeeze the bottle, and we're going to talk about what happens once I squeeze the bottle. So, let me squeeze the bottle down here, have my hands on it, and squeeze. So here's what's actually happening. If you notice, you actually zoom in just a little bit. I don't think this thing was perfectly tight. There we go. If you actually zoom in, what will actually happen after a couple of minutes is the temperature inside this bottle will actually begin to rise. And the reason why the temperature inside the bottle will begin to rise, it was on 1864, now it's on 2068. There we go, it's on 2068. Well, the reason why the temperature inside the bottle is rising is because when I push this, when I squeeze this, I've just compressed the air inside here. I've packed it into a tighter space. This happens whenever air sinks. When air sinks and you squeeze it and it compresses, that actually tightens the space and that actually causes warming. On the other hand, I've just let go of the bottle. And let's give it a moment. Usually it's not as quickly evident here, but what usually will happen is that the temperature inside the bottle will actually go back down to the original temperature. Usually it's not as quick in this time because I've had my hands all over the bottle, and that creates heating, and so you get lots of heat from the hands that ends up conducting into the bottle. So I'm not going to focus on this too much. If you wanted a really good example, maybe a bigger bottle would be better. Another good example, though, is about this hairspray right here. This is Tresemme Extra Firm Control Hairspray. I don't really need it right now. Definitely not right here. But, so what this is this is actually a liquid that has been compressed into this canister at the ambient temperature of this room. So this liquid is the same temperature of this room. But if I were to shake it up and spray it on my arm, I actually felt it to be a lot cooler when I did that. And the reason why is because all of that compressed air, when it shoots out, it expands. And that expansion causes cooling. Now, if you don't believe me, with your parents' permission, or whatever, if you're over 18, go get a hairspray canister or a canister of compressed air, and just for a second, don't do it for long, just spray it on you, and see what happens. It'll actually feel pretty cold. And again, the reason why is because this air was compressed. When it shot out, it expanded, and expansion leads to cooling. We actually check back on the bottle. Actually, here we go. Check back on the bottle. Can't see it too well, but it's actually back down to 18. Okay, so basically what I want you to get from this is when you squeeze something, when you squeeze air, that causes warming to occur. When you allow it to expand, that causes cooling to occur. So as air rises in the atmosphere, it actually will expand. It's entering an environment of lower pressure, causing it to expand, causing it to cool. Now with that said, there is moisture inside this bottle. And what actually happens is, inside this bottle, some of this water is actually evaporating as we speak. And that's actually raising the dew point temperature inside this bottle. Since there's more evaporation occurring, higher dew point temperature. And since there's a higher dew point temperature, the air here is becoming more and more and more saturated. Eventually it actually reaches saturation. And then what I can actually do is raise the temperature inside this bottle. That causes a little more evaporation to occur, and then let go. That's going to cause it that's going to cause the air to immediately cool, and that's going to create a cloud. Now with that said, in order for you to get a cloud, you need 3 ingredients. 1, the water bottle, 2, the water, and 3, some kind of solid aerosol particle. Now I'm in my office here at De Anza College, so I'm not going to burn anything. Like smoke is usually the best example of this. And smoke is the one I would recommend using. Take a match, light it, put some smoke in here, and then squeeze and let go and watch what happens. But I'm not going to do that. So I'm going to use, first let me get this thermometer out of here. If I'm lucky. Yay, I got it out. Okay, so what I'm actually going to do is this same canister is what's called an aerosol can. And what that actually does is there's actually some solid particles in here that act as aerosols that then the liquid droplets in here connect to. They actually condense on it and spray out. So what I'm going to do, okay, done. So now what I just did is I just sprayed a little bit in here, and so I'm going to give it a moment to kind of swish around. So what I've just done is I've added some particulate matter in here, some what is called condensation nuclei, solid particles that water vapor can stick to as it condenses. Now here we go. Make sure it's nice and tight. Squeeze, and let's do that one more time. Squeeze this time. I'm going to hold it for a couple of seconds. And do you notice, one more time, squeeze, and if you actually take a look, the air inside here actually...
Hello? Terrence, where did you go? Did your iPhone break or something? Oh no, what happened? Oh wait, yeah, when I was recording that, my iPhone ran out of storage, so I actually had to delete some stuff real quick and then jump right back to it. I don't have, obviously, the biggest budget in the world for video production, but good enough. That's okay, here's part 2. I'm back now. Yay! And back to it, Terrence.
Okay, I'm back. So apparently my iPhone ran out of storage. Don't you hate it when that happens? I promise I didn't do anything magical to the bottle. But if you actually take a look, the bottle now looks pretty hazy. But watch what happens when I squeeze it again. So what happens is when you squeeze it, you're actually warming the temperature inside the bottle, causing any water vapor inside to evaporate, or causing any liquid droplets inside to evaporate. Now watch what happens when I let go again. The air inside gets really hazy. And that's because those water droplets have now condensed, or sorry, that water vapor is now condensed into liquid droplets. It's now condensed into liquid droplets. So one more time, just for good measure. One more time, just for good measure. And there we go. So if you want to do this at home, all you need, water bottle, little water at the bottom of it, lid, and then some kind of smoke or aerosol spray, some kind of condensation nuclei. And then, there you go, cloud in a bottle. Take it away, Terrence.
Well, thank you, Terrence. So that's it right there, and that's also it for my corny joke of me talking to myself. So I guess if you get nothing else from this video, you can tell people, my teacher talks to himself. So yeah, that's basically what happens. Basically, when air compresses, it warms, and any moisture, any liquid droplets can then evaporate. On the other hand, when air expands, it cools, and any moisture then condenses, creating a cloud. And so that's just how you do it. Simply, bottle of water, just a little water on the bottom of it, some kind of smoke, aerosol, something like that, just so you have those condensation nuclei. Put the lid on top, give it a good squeeze, give it a few seconds for some water to evaporate, let go, boom, you got yourself a cloud. Now, how does that actually apply to what we've been talking about in this class? Well, here's a map. This is actually not the same map that you're going to be working on for today's exercise, but close enough for jazz. And basically, what you're going to be looking at is at different locations, you're going to be comparing the air temperature, right, nya, to the dew point temperature, down, nya. And what you notice is that when the air temperature and the dew point temperature are not equal, that means that the air at that height, specifically at the surface, is not saturated. Now, that doesn't mean that there are no clouds above you. That just means there are no clouds at the surface. There could still be a moist layer above you. So, for example, over here in eastern Nevada, so I'm trying to remember, I think this is Winnemucca. I don't remember from the top of my head. Might be Elko. Don't hold me to that. If I had to look it up for a second, I would. I'm just kind of pulling it out right now. But what you actually see here, so let me get my cursor again. The air temperature is 44, and the dew point temperature is 34. Now, with that said, they are not equal. Therefore, the air at the surface is not saturated. Yet, if you actually take a look on the inside, that circle is completely shaded. That means clouds are present. They're just not present at the surface. Now, if you wanted to find out where clouds are present, you can actually look at ye olde Stuve diagram. Now, up to this point in this class, we have been primarily focusing on the line to the right, air temperature. But today, we're going to talk about the line to the left as well. That is the dew point temperature. And as I mentioned, when they're equal, clouds are present. Dew point temperature, air temperature are equal, the atmosphere is saturated, and you have clouds present. I actually took this from, this was actually a weather balloon launch at Oakland International Airport. And actually it was done almost at the same time as this weather map. And this is San Francisco, which is just right across the bay from Oakland. And the temperature's 53, the dew point's 47, and you have some clouds. But because the temperature and the dew point aren't the same, the clouds aren't right on the ground. So where are they? Well, and if you notice down here, you compare the temperatures to each other, there's a little bit of a gap between them. The temperature and the dew point are not the same. However, as you rise in the atmosphere to approximately 930, 935 millibars, so right here in between 950 and 900, you actually notice that the air becomes saturated. Temperature and dew point become equal to each other, and the two lines are now superimposed on top of each other. That represents a cloud layer. On the other hand, as you rise up, you then get a region over here where the temperature and the dew point are very different from each other. That represents a dry layer. There are no clouds present there. So clouds are present whenever you see the two lines very close to each other, not present when you don't. And how does this relate to the whole cloud in the bottle thing? Well, down here, the temperature had cooled to the dew point. So down here, the temperature had cooled to the dew point. Up here, the dew point, for some reason, became much cooler, probably due to advection. So basically what happens here is that air has actually, some dry air has actually moved in over this region, and so there are no clouds present there. So that's really it for this module. One of the things is when you look at a map like this, they may say, and so regions are seeing varying degrees of cloudiness. Anywhere where this circle is at least somewhat shaded, that represents varying degrees of cloudiness. Either cloudy, mostly cloudy over here, partly cloudy over here. Those are all varying degrees of cloudiness. That means there's some kind of cloud in the sky. Meanwhile, up here, you see lots of empty circles. These are clear skies. But that's it for this lab. As always, if you have any questions, please feel free to reach out to me. And I actually also have those 2 cloud in a bottle videos on YouTube. And I will mention, very honestly, my iPhone storage just filled up. I tried to do it on my computer, but it looked very choppy, so I went with the best technology I had. Thank you for watching. I actually hope that you do that experiment on your own. Really, just a 2-liter bottle and some water, a lid, and some kind of smoke. And that's it. So again, if you have any questions, comments, concerns, please let me know. Take care and good luck on this investigation.